Hello everyone. I and my colleagues are going to discuss about what is flip-flops, especially the JK flip-flops. Okay, let's start with a brief introduction to flip-flop. Do you know, computers and calculators use flip-flop for their memory. A combination of number of flip-flops will produce some amount of memory. Flip-flop is a form using logic gates, which are in turn made of transistors. Flip-flop are basic building blocks in the memory of electronic devices. Each flip-flop can store one bit of data, and they are also called as sequential logic circuits. Flip-flops have two stable states, and hence they are bistable multivibrators. The two stable states are high, the logic 1, and low, the logic 0. The term flip-flop is used as they can switch between the states under the influence of a control signal, clock, or the enable. That is, they can flip to one state and flop back to other state. Some of the most common flip-flops are the SR flip-flop, set to reset, the D flip-flop, the data or delay, the JK flip-flop, and lastly the T flip-flop. Latches and flip-flops are both 1-bit binary data storage devices. The main difference between a latch and a flip-flop is the triggering mechanism. Latches are transparent when enabled, for areas, flip-flops are dependent on the transition of the clock signal. That is either positive or negative edge. The modern usage of the term flip-flop is reserved to clock devices, and term latch is to describe much simpler devices. Some of the other differences between latches and flip-flops are listed in below table. Latches do not require clock signal. However, flip-flops have clock signals. A latch is an asynchronous device. A flip-flop is a synchronous device. Latches are transparent devices, that is, when they are enabled, the output changes immediately if the input changes. A transition from low to high or high to low of the clock signal will cause the flip-flop to either change its output or retain it depending on the input signal. A latch is a level-sensitive device, and a flip-flop is an edge-sensitive device. Latches are simpler to design as there is no clock. However, flip-flop compared to latches, are more complex to design as they have clock signal and it has to be carefully routed. The operation of a latch is faster as they do not have to wait for any clock signal. Flip-flops are comparatively slower than latches due to clock signal. The latch have a power requirement of a latch is less. However, flip-flop power requirements of a flip-flop is more. Latch works based on the enable signal. Flip-flop works based on the clock signal. JK FlipFlop is named after Jack Colby, an electrical engineer who invented IC. The JK flip-flop is a modification of SR flip-flop. In this, the J input is similar to the set input of SR flip-flop. The K input is similar to the reset input of SR flip-flop. The condition J is equals to K is equals to 1, which is not allowed in the SR flip-flop. S is equals to R is equals to 1 is interpreted as a toggle command. This is a JK flip-flop integrated circuit. The JK flip-flop has the following. It has two data inputs J and K, one clock signal input for the clock, two inputs Q and Q bar. The symbol of a JK flip-flop is shown at the left. The circuit of a JK flip-flop using gate is shown. It is similar to modified NAND SR flip-flop. Here is the truth table of a JK flip-flop. When J is low and K is low, then Q returns its previous state value, that is, to hold the current state. When J is low and K is high, then flip-flop will be in a reset state, that is, Q equals to 0, Q bar is equals to 1. When J is high and K is low, then flip-flop will be in a set state, that is, Q is equals to 1 and Q bar is equal to 0. When J is high and K is high, then flip-flop will be in a toggle state or flip state. This means the output will be complement to the previous state value. Now, let's apply this to our sample problem.
For the example of JK flip-flop, given the waveform for J and K, the question was, sketch the waveform of Q. So here are the following steps to answer that problem. First, Put 1 or 0 value on J and K input. Remember that the low line represents 0 and the high line represents 1. That's what's indicated in the given. After putting the value, by each column, get the value for J and K. Make sure that you memorize and be familiarized in the truth table for the JK flip-flop. If the input are both 0, the state was no change. If the input of J is 0 and K is 1, the state was reset or start again to 0. If the input of J is 1 and K is 0, the state was set or start with 1. If the input is both 1 in J and K, the state was complement, which means whatever the previous value, the next value is the complement of it. For example, if your previous value is 0, the complement of it is 1. Or, if your input is 1 and the complement of it was 0. After getting the value of Q, the next step is to plot it. Plot the value of Q and the answer is just like this.
For our next example, let's answer the timing diagram for positive edge triggered JK flip-flop. Example number 2. Let's start at column number 1, as J and K inputs are both 0. As the truth table says, it is at no change state, so we started at 0. In column number 2, the J and K inputs are 1 and 0 respectively. We will base again at our truth table. It will give us an output Q, A1, so it will be a set. In column number 3, J and K inputs are both 1. So as the truth table says, that the present state will be complemented or inversed. Column number 4 is same with column number 3. So we just complement the present output 0, giving us an output 1. In column number 5, as we can see, the inputs of J and K are both 0, 0. Based on our truth table, 0, 0 are no change. So our output is 1. In column 6, as we observe that we have two inputs of K, which are 0 and 1. As we plot the line, at first input 0, 0, the present output of 1 will remain. And the second input 0, 1. Which will give us a reset output of 0. Column number 7, J and K have an inputs 1 and 1 respectively. As we look at our truth table, it indicates that 1 and 1 will give us a complemented output of 1.
Where we use flip-flops. Flip-flops are widely used as registers in electronic devices like computers.
As counters to count the increment and decrement. As data transfer, and as shift registers from one flip-flop to another, as frequency division, which divide the input frequency to its half.